Okay, everyone, welcome to Stateless Implementers Call number 31. I've shared the agenda link in the chat, so anyone can read that. So the agenda for today is first having the usual team updates. Then I will do a pre-image file generation presentation. Then we'll touch a bit on the Ethereum Stateless book announcement that happened some days ago. And then we'll wrap up with the multi-client state conversion topic. So yeah, let's start with team updates. I can start. So personally, I've been working, well, in this pre-image file generation stuff that I will present in some minutes. And I've done a bunch of writing for this stateless book. So yeah, that's mostly from my side.
Yeah, I've been on holiday, so not much. Just also did some writing on the book, or more exactly, a lot of reviewing. And we were also engaged in trying to get more specifics in terms of what would a binary tree proving system would like. Still an ongoing effort. Yeah, I think that's pretty much it for now.
On Bezu, so we made some progress on the stateless part. Thomas still working on the state reconstruction and the proof verification. I had to switch on the transition, so I just started today. So I will try to set up something, a first implementation like that. We will be able to do this transition with Bezu, maybe more in the coming weeks. And yeah, it's mainly that. We did also some modification in the gas cost part in order to be able to manage atomic and no atomic implementation. So, and we fixed also some issue on this part. Yeah, it's all on the Bezu side.
On Ethereum JS, we have merged our binary tree implementation along with some tests, some of them coming from the Python from Ignacio, and some new ones that we came up with to test some random output and get operations and things like that. We are now working on creating like better documentation for it so that if people want to play with it, they can. And also working on creating a state manager that will allow state management with an underlying binary tree structure.
Anyone else want to share some updates? If not, we can move to the next agenda item. Okay, so the next item is pre-image generation file or research. So I will share my screen because I have some slides. 1 second. Okay. Hopefully you can see my screen.
Yep.
Yeah, okay. So yeah, so this presentation that I will be doing is based on this ETH research post that I wrote some days ago. So if you want to see the full explanation, probably you should read this thing. But let me share a bit more like a high level explanation. So, okay, let's start with a bit of what this is about. So we already know that if we are going to change the state tree, we have to do this state conversion, which is basically moving data from the existing tries to a new try. And this task has some kind of orthogonal challenge, which is we need the preimages of Ketchak for really doing this task. So a bit of motivation and background. I think that most people in this call already know about this, but I think it's worth a refresh, or maybe somebody else maybe doesn't know it. So as I said before, the motivation around this preimage file generation is based on this intention that we have on changing the current Merkle-Patricia tries with a new tree, that being a Merkle tree or a binary tree. It doesn't really matter for this problem in particular. And the problem with this is that basically for moving the data from the old try to the new try, you basically have the keys of the existing tree are hashes, are Ketchak hashes. And for calculating the new key in whatever new tree we introduce, you need the preimages. And the main problem is that today, the majority of clients do not have this information. So the LDR, somehow we need to provide this information to all the clients before this conversion starts. So double clicking a bit on why clients do not have this information. Basically, the point is, from a specs perspective, the three keys are actually the hashes. So apparently, there are no motivations for clients to actually save the preimages, which basically led to many clients not really storing this information by default. If you enable some flags, they can record these preimages, but this isn't the default behavior. So to look at some cases, like many clients have some flat DB for accessing the state faster than using the tree. And in these cases, for example, Get has a flat DB, which the keys are actually the hashes, the same hashes as the tree. So from this flat DB, you cannot really get the preimages. Other clients, such as Aragon and Red, have designed the key of this flat database differently, and they actually use the preimages. So on these clients, you can actually know all the preimages of the current state. So technically, these clients could do enough work on themselves to get all the preimages. And other clients, such as Nethermind, don't have like a flat DB yet. So they don't have the preimages. But yeah, depending on what they end up introducing, because they are working on this, I think they won't have it anyways. So yeah, the TLDR is that most of the network don't have these preimages, and we have to find a solution to generate this information and spread it through the network. So where does this preimage thing fit into the big picture? If you want to like ultra simplify the problem, we have Ethereum today, which has all the state in the Merkle-Patricia try, or tries, I should say. And we basically want to, kind of wave a magic wand and somehow have a reality where we have the new tree with all the existing data and call it a day. Of course, things are a bit complicated, and this magic wand is requires some effort. So here I basically show the current idea that we have discussed before in multiple SIG calls. And the idea is that this magic wand is basically doing two things. The first thing, or what I call here the stage one, is a fork in which we introduce an overlay tree. which basically means having a frozen MPT and a new fresh tree on top. And yeah, just only doing that. So as we keep executing blocks, we only write to the new tree and keep the old tree read-only. And then at some point in stage 2, we actually start the conversion process. So if we kind of zoom in into this stage 1, and what that means is, as I said, we have the EVM, we have this overlay tree that is introduced at this point in time. This overlay tree is basically this new state tree, by Merkle tree or binary tree, doesn't really matter. And we have the current MPT, which is read-only. So the way this works is basically the EVM, whenever I have to do a write, it does this in the new state tree. And whenever I have to do a read, it tries to read from the new state tree. And if it is not there, it will have to read from the Merkle-Patricia tree. That's kind of the TLDR. Now, after this is done, as I showed here, that was stage 1, we have to do this waiting period. So this waiting period is basically waiting enough blocks for this read-only MPT to finalize, so we know that no blockchain reorg will change this fact, which simplifies a lot EL client implementations and also pre-image generation. Then this is stage 2 that I showed here with this black rectangle. It's basically all this other EIP, which describes the conversion process, where basically you have the same setup as before, but what you do is on each block, you add this new rule in which you move X entries from the read-only Merkle-Patricia tree to the new tree. So what does this mean? It's basically something that I show here is we define a way of walking the Merkle-Patricia tree and say, do this deterministic walking and migrate X conversion units from the old tree to the new tree. Keep doing that on each block. And at some point, since this tree is read-only and frozen, you will reach a point in which you will end up moving all the state. Now, it's at this point in time that when we are doing these movements, we kind of read an entry from the existing tree, which basically describes a key, which is a hash of something. We need that something to really rehash and have the new key in the new tree. So for doing this step, we actually need the pre-images of the tree. That's where this pre-image file appears. Okay, that was a bit of context. So this presentation kind of zooms into this pre-image file and what it means and multiple angles of it. So I will be talking briefly about distribution, verifiability, generation and encoding, and usage. So the main focus is actually generation and encoding, but I will be talking about these other things just for completeness. So regarding distribution, this is something that we have talked about, I think, last year in multiple C calls. But the point is, okay, we don't know yet how this file is generated, how it is encoded or whatever, but at some point we have to distribute the information to all the clients in the network or most of the clients. And yeah, how we do that really. And there are multiple options. We have this option, which is the most pragmatic one, which is, let's generate a file, upload it to multiple CDNs, and just people will have it available to download this file before the conversion starts. There are other proposals using maybe protocol channels. So we have like an in-protocol way of sharing this information. Or there were other ideas about, kind of packing the needed pre-images per block. So this information is bundled per block, so you don't have to really download anything before the conversion starts. Each option has different trade-offs. It's not the point of like this presentation to dig into all this, but currently the main consensus seems to be the pragmatic one of just uploading the file to multiple CDNs, and yeah, because this is like a one-time thing, so we have to think about like complexity and any kind of technical debt that is left into the protocol too. On the verifiability side, let's assume that we are downloading this file from some CDN or whatever. Of course, these CDNs aren't trusted, or there can be some kind of hacked supply chain. Maybe whoever uploaded this file chose the wrong file, or is invalid, incomplete, corrupted, intentionally or unintentionally. So the problem with having an invalid file, the problem with like just downloading the file and assuming it is correct, is that whenever the conversion starts and you have to start using it, if this file is not correct, you will be blocked at some point, and that will be pretty bad because it means that you won't be able to attest, and that will be pretty bad. So we need to be sure that this file is verifiable. And there are like two main strategies for this. We have like the fully trustless one, which is you download the file, you actually go through the walking of the tree, you verify that every tree key that you will move is actually like this file actually has the preimage. And you have to do this before the conversion starts completely, because yeah, if you do that and you verify that all the information that you will need, it is there, you are guaranteed that to be safe and that you won't be blocked in the conversion process. Of course, you have to do this after the Merkle-Patricia try is finalized, so you have that guarantee, because since the tree is read-only and frozen, it's a safe assumption that in the future, yeah, that check will be valid. Another more like pragmatic approach is saying, okay, maybe some of your clients will simply want to check this file themselves and bake into the client a hash of the file. So the client will actually download the file, just hash the entire file that was downloaded and check that hash check matches. So from that perspective, we are kind of trusting the EL client team, but this kind of check is much faster, right? And so yeah, I know this will be up to each EL client, I guess, but you have those options. Okay, so let's move more into how to generate this file, how we encode the information, which is the main intention of this presentation. So if we think about how to solve this problem, like the ideal encoding will be an encoding which optimized for the expected reading pattern. As mentioned before, the walking algorithm for the way we have to move data is known. So we actually know which preimages we'll need in which order, and even in each block, right? Because how many things we move per block is a fixed number. So yeah, ideally, the way we read this preimage file should be aligned with that reading pattern, so you can have the lowest amount of overhead from the resource perspective. Another thing is, yeah, ideally, we want this file to be as small as possible. I wouldn't say this is like an incredibly critical constraint, because this is a file that you only download once. But yeah, I mean, if it is as small as possible, it's better than if it is bigger. And as I said before, ideally, we want to make this generation and encoding not really be complex, because it's like a one-time thing. If we kind of come up with a really complicated encoding for the file, everyone will have to implement that. We have to, test it a lot, do some fuzzing and all that. So the more complex the encoding is, and the more work we have to do to know that we are safe. So there's like a super simple and obvious encoding for this file, which is the one I show here in red. So the encoding is actually incredibly obvious, and it's just appending to the flat file the bytes of the preimages. So for example, when you start the conversion process, you start with the the account try. So the first thing that you will move is some address A. This address A might have a storage try, so you continue in that storage try, and the first key in that storage try is some storage slot A, so you put the bytes for that, and then you continue with slot B for that account A up to maybe that's the last storage slot. You continue the walk with some other address B, and you continue with the storage try. So this is basically putting the 20 byte address A, then 32 bytes of storage slot A of address A, 32 bytes of slot B of address A, and it's simply like the minimal amount of things that you have to add to really provide information. This encoding doesn't have any overhead. Like this is like the minimal amount of information that you need. There's no like prefixes or something like that. This is not entirely needed because even if address A is 20 bytes and storage slots are 32 bytes, whenever you are working the tree, you already know which kind of preimage you need to read. If this is a storage slot or it's an address, so the reader already knows if it has to read 20 or 32 bytes. So there's no need to really put a prefix here, which is really nice. And the other benefit is that you are doing a linear forward-only read because the order of this stuff is actually the walking order. So that's really nice because you simply read this linearly, which is really nice for disks. So I created a tool for actually generating this file with this format. You can see the link here. I basically use a Ref node database. It doesn't need to be an archive node. It's just simply a full node. And yeah, you have like a preimage tool, and you have some commands. So there's like this generate command which basically generate this file. And there are some other commands for other things. For example, the verify command where you can have a block. You can have this, for example, downloaded file from somewhere, and you simply verify that this thing is correct. And this other command is for something else I will say later. Let me check the time. Okay, I will move a bit faster. So if I generate this file with this format, the generation time is 1 hour. The uncompressed size is 42 gigabytes. And if I compress this simply with STD, this compresses to 36 gigabytes. So that's kind of the big picture. Now, there's like a fair question, which is, okay, which is the encoding efficiency of this? Because if we look at the format, we know that everything that is an address something, so any address, isn't duplicated because whenever you walk the account try, all these accounts aren't duplicated, so that's fine. And some value address X can be compressed because it's basically a hash output. So, I mean, this is not compressible information. So from that perspective, address X things in this file, we can't do much about it. Now, for storage slots X kind of values, they are duplicated because, for example, there can be 2 accounts that both use the same storage slot. So that means that the file will have multiple times the storage slot, for example, 1. So this is duplicated information, and actually the preimage is a 32-byte big endian encoding of this number. So this storage slot number 1, we have like a lot of zeros, right? So there's like a lot of compression opportunities. Not only for like 0 prefixes, but for example, even if you have an array which is the entry in a hash map. So like the actual base address is pretty random. All the entries of the array will have the same kind of prefix. So yeah, there are other kind of compression opportunities. So in this same tool, I did this storage slot free command, which tries to dig into these details. And here I'm showing the top 20 results. So let me explain what this is doing. What I'm doing here is basically saying, okay, I want to know from all the pre-images of this file, how many repetitions I have for a 29-byte prefix. Okay, so the idea here is, for example, all the storage slots that are top-level contracts variables will be in storage slots 0, 1, 2, 3, 4, 5, 6, or whatever, right? So all those will have this prefix, which is basically 29 zeros. And the last 3 bytes will be, will change, right? So if we look at all the file, we have around 55 million entries, which accounts for 1.5 gigabytes of the file. Here's like a relative measurement. For example, the second item, most repeated prefix, is this thing. And if you think about it, this prefix corresponds to the Keccak of storage slot number 8. So this is basically showing that, for example, arrays which are at storage slot number 8 are like on the top, are like the second most repeated pre-images. Because yes, this array will have multiple entries, and all or most of the entries will have this prefix, right? So this accounts for 13 million. So I have here like a cumulative thing. So if you move down, you kind of start seeing like how much the top n prefixes account for the total size. If you want to see the full output, there's here in this link where I show the full 1,000 things. It's a pretty long thing, but already like seeing this percentage, you can see that there's no like low-hanging fruits, and the tail is pretty long. So I think that's good to have a sense of what the things are. Okay. So coming back to the encoding, we can have this option 1, which is, okay, let's not really do anything else and simply use this ultra simple forward read-only encoding. Using STD for compressing the file already compresses all these cases in a kind of automatic way without any extra implementation effort. And it saves around 6 gigabytes, right? Now, another option is saying, well, actually, I want to do some custom dedupe encoding to really try to come up with some clever way of solving this within the encoding format. So we will remove this automatic compression because the encoding itself, we will try to do the deduplication. My take on this is that might not worth it, because if you look at the file and you look at the top 1,000 storage slot prefixes and you go to the bottom, that accounts for around 4 gigabytes of saving. So there's no like a clever way of saying, yeah, let's simply dedupe the top 100 prefixes, and that's kind of enough for getting something better than just compressing the whole file. So I think that my take on this is, it might be better to maybe simply go with the simplest option. Of course, we have to discuss this at some point, but yeah, the automatic compression already goes further than compressing the top 1,000 prefixes. So yeah, that's kind of the kind of insight I wanted to have, to really look at these pre-images and have a sense of how much it is worth going with something more complex. Okay, and finally, regarding usage of this simple encoding, yeah, as I said before, it's only forward read, so EL clients, whenever they use the file, can keep a kind of a cursor of which is the current place of the file for this block. So this is really nice because if you have some kind of chain reorg, you can simply seek the file into some previous place that you already know. So handling reorgs is pretty simple. You can also do some kind of preloading, so you kind of load in memory the next 100 blocks. So you don't even have to go back and forth in the file to handle reorgs or amortize these grids with time instead of doing one per block or similar. And if you want to go wild into saving disk space because you have to, somehow store these 36 gigabytes or whatever, I know maybe after some finalization point of the chain, you can start deleting all entries of the file and save some space, but I don't know if it is worth it really. So yeah, that was the presentation. Thank you for your time, and I know if anyone has a question. Yeah, Goti.
Just one quick remark, maybe I misunderstood something. But if you go back to your slide, basically with the format where you basically say you just concatenate all the pre-images in the order that the client is expected to use them. But these pre-images have different sizes, right? Depending on the type of data that actually gets reorged, whether it's an account slot or a storage slot, right?
Yes. Right, correct.
But I mean, I'm just wondering because I mean, whether if you do compression anyway, whether it would be better to just use the same length for everything. Because as of now, having a different size here has two downsides, which is that in case of a reorg, if you said you can use a pointer or just something into your file, but the problem is if you basically go back, you need to know how far you get back into the file, because if you go back, I don't know, 10 units, you need to know how big those 10 units are in actual bytes, which depends on the type that you just read in the last 10 slots. So it's actually a bit more complicated here. Rather than if you just had the same size for each data item and just prefix it with zeros, you would just know, oh, I need to go to this position in the file, which is arguably easier from an implementation point of view. And the second problem is if you, I mean, it's fine if you use the CDN route of distributing the pre-images, but due to the fact that these files have different lengths, it gets much more complicated if you want to sort of chunk up your pre-image file into several chunks and verify them individually. Because it's hard to sort of seek into the correct position if you don't know sort of the offsets coming from the different lengths. And if you're using compression anyway, I would expect that just prepending sort of the shorter pre-images with zeros, just to pad them, the cost in sort of distribution gets pretty much away because sort of the compression algorithm would probably take care of that. I'm not sure whether this is a better idea, just something that I would think maybe easier actually from an implementation point of view.
Yeah, I totally agree with that. Because if we use some compression for the file, making each pre-image have the same size will definitely simplify the cursor thing, because moving back only depends on the number of conversion units you do per block, instead of that plus which kind of entries you like that block has. So and the compression thing will basically remove all that like overhead. So I think that's an interesting idea to simplify stuff.
Just regarding the reorgs, that's actually not true, because we save, if we have a reorg, we have a pointer to where the block started reading. So this is saved. So we can, I mean, at least we have an efficient and easy algorithm to do this. So the reorg itself at least is not the problem.
Yeah, sure. I mean, you can do it. It was just it's easier to do it because you don't have to. Just it's more easier way to do it.
I think there was a third point. I just don't remember what it was. Like there was the compression, there was the reorg, and you said something else.
Yeah, if you sort of distribute the pre-image file sort of into chunks, then you would want the client to get, I don't know, the third chunk of the pre-image file. You would want to be able to verify that chunk individually without knowing what the first two chunks are. And for that, you need to know sort of where in the total file this thing starts. That is harder to get unless you include some additional information where it starts into individual chunks. It gets harder. I mean, if you go via CDN, it's not a problem, but if you sort of do other routes, it gets more complicated.
Yeah, so we didn't think about distributing it in chunks. That might be an option. We just haven't considered that. At least I didn't. But I would say in that case, what I would do is add the header to which account, right? Okay, maybe to clarify, the verification is pretty simple. You just start in your database at address 0, and you go over the file. And as you go over the file, you go over all the key values in your snapshot or your flat DB.
Yeah.
So if you do the same thing, if you do with chunks, instead of starting at 0, you could have a header that says this chunk starts at hash so and so, and you could do the same thing. Yeah, okay, I guess we could do this. That wouldn't be, at least that would be workable.
Yeah, I mean, it's definitely workable. I mean, it was just a comment that it would be easier if you just use the same size. Not that it's not workable, because you wouldn't need that header.
Yeah.
Does anybody else?
Sorry.
Yeah, go ahead. Sorry.
No, I was just thinking, I wouldn't know if, like, for example, you had a chunk that was, stopping in the middle of the contract storage, but I guess you could have 2 hashes instead of 1. And yeah, okay. I think, okay, let's, yeah, I don't want to hog the call. I think it's workable. I just have to think about it.
Yeah, I think at some point we have to resume this conversation about if this CDN seems to be the right. I mean, I have the sensation that until we discuss this in ACD, we will never know for sure. These are the kind of things that are pretty hard to be sure about until like the real discussion happens. But from what we have discussed in previous SIG calls and in the last DevCon with Guillaume, we met with Piper and other people from the Portal network. It seems to be that most people seem to agree that the CDN might be like a pragmatic way of solving this. But yeah, probably we won't know until we discuss it in ACD. So that's pretty tricky. Okay, the next agenda item is the Ethereum Stateless book. Maybe Guillaume, you want to mention something about that?
Yeah, we wrote we wrote mostly Ignacio. I was just reviewing the Stateless book, so it's at this available at okay. Ignacio already gave the link, stateless.fyi. Maybe if I can share my screen, I can go over it quickly. It's always the question. Here we go. Can you see my screen?
Yep.
Yes.
Okay, cool. Yeah, so we basically start with something fairly simple, like why, what is the reason for stateless? We discovered there's a lot of people that, are not working on the stateless topic day to day, and they're asking questions. So, of the utility of stateless. So we have some ideas. We have a few things, like we go over the design of the trees, so how we encode the data in the tree, how like we have we go over the 31 byte chunk model. We want to add the 32 byte chunk model later. So it's a living book. It's not complete, but nonetheless, we talk about vertical trees. We talk about binary trees. We talk about the block hash situation. We talk about AIP 4762. Why we had to remodel the gas and what does it do basically. We talked about the state conversion, so I guess that's going to connect to the next topic. But we explain we give explainers about the EIPs, the pre-image distribution that Ignacio just talked about, and then there's a series of use cases that we are going to expand in the coming month, as well as a series of resources. I mean, most of them should already be known to you. They're taken more or less verbatim from the old Verkle.info website. And actually, I'm not sure. Oh yeah, right. And we also have information about the current devnets, how to run the execution spec tests. If you want to contribute, I mean, you guys should not need this, but people who want to contribute might look into this. And of course, there's a summary of all the previous SIG calls, except this is the first. Oh no, right. This is the history. So we have the list of all, or at least we want to list all the previous SIG calls. And I don't know how far it goes actually. Do you know, Ignacio? I mean, you wrote it. Yeah, okay, so we started call 2020 first. Okay. Yeah, so that's pretty much it. If you're not aware of that already, have a look. It's quite good. And if it's missing something, of course, let us know.
Yeah, I just want to say that this repo is public, so we are inviting people to collaborate or fix things. So feel free to open PRs or whatever. Okay. Next and last item is multi-client state conversion. Yeah, maybe Guillaume, you want to lead this one. I'll give a bit of context on some conversations we have been we have with the research team about the future and all that, so which are
Yes.
like a good way of moving forward.
Yep. Yeah. So we want to have some. Well, we did have some conversation with the research team, trying to make sure that what happened with Verkle does not happen again, and trying to fix the roadmap, maybe not entirely, but at least well enough that we can work. We can, deliver something, like clients can deliver something without having taking the risk of having to start again in 2 years. And one of the, I would say, decision points, although that's not really up to the research team to decide. I guess it's, I mean, not alone. It's more like an ACD conversation to have. But at least one agreement, or agreement of what how the decision can be taken, would be to demonstrate that that the conversion is easy to do, which I can tell you as the sole implementer of the conversion in Geth. Well, actually, sorry, Ignacio, it's teamwork. But as the sole team who implemented the conversion so far, we know it's fairly easy, but we want to prove that it's easy if you do it in a multi-client context. So yeah, we would like to invite you to focus on implementing the conversion, and ideally we would be able to demonstrate some kind of shadow fork in the next ideally 3 months, but 6 months at the latest. That should be doable. So I mean, feel free to dissent. But from what I understand, it should be fairly easy to manage. We can of course provide support, and yeah, if I'm sorry, I forgot my train of thought. But yeah, like basically we want to focus on that, maybe more urgently than working on the next testnet. And so if we could get this done, I think that would go a long way to prove that the model of stateless, well, probably with binary trees, is the viable one for having a stateless fork late 2026 and more realistically, early 2027.
Before testing the state conversion, should we, do we have a finalized EIP for that? And should we do it with Verco as a target, or are we aiming for binary as a target?
So it doesn't really matter. I would say Verco because indeed, like the whole binary tree, there's a lot of things to still flesh out. What proof are we using? What proof system are we using? What hash function are we using? We want to target Poseidon, but Poseidon hasn't been proven. It never will be proven secure until it's broken. But at least the effort that the Ethereum Foundation is currently leading to break Poseidon is ongoing and is going to take at least 1.5 years, if not 2 years. So I think currently everybody or most clients in this room have implemented Vercal trees. There's no urgency to replace it. Like I said, the EIP, the tree structure itself is pretty easy to implement, and the proof system is completely undefined. Whereas for binary trees, whereas for Vercal trees, the tree structure is well known, the proof system is well understood, it's already implemented, and the idea is that you can switch, like the design of the binary tree EIP is designed in such a way that you can swap binary trees, like Vercal with binary trees, in no time or very little effort. So it doesn't really matter. And I think at this point, Vercal is still the way to go. Yeah, Ignacio.
Yeah, I want to touch on a question that Spencer did in the chat. And yes, I'm planning to start working on execution spec tests for the conversion. Last year, I wrote a HackMD doc with all the test cases that would be worth testing. So I kind of already explore like all these kind of border cases and things like that. So I can start working actually implementing these tests so I can give like these fixtures to clients and we can actually test implementations without launching devnets and things like that, which is, yeah, pretty nice for everyone to move faster. So yeah, the answer is yes, I guess, Spencer.
Yeah, please get in touch.
Okay. Anyone else want to mention something else about this topic or any other topic? We have some 10 minutes before the call ends. If not, we can finish early.
Yeah, I just have a quick, maybe something to add. I don't think I missed it. There's, if you look at the EIP of the conversion EIP, we translate the code, sorry, the storage before we translate the account. And in the binary, like flat file format, it's the other way around. The account comes before the storage, and I got confused for a minute, but we need it this way, right, Ignacio?
I got lost a bit. Why does binary matter here?
No, there's no binary. It's just the conversion itself.
So you're saying that we first migrate the storage in the IP, right?
In the IP, we first migrate the storage, and then we migrate the account. But in the flat file, it comes.
Right. So yeah, I agree. It comes first the account and then the storage. So for a linear read, we will have just flip this order. Yeah, I mean, I don't have like any pushback on that. I don't know if that's the case for every client. I guess this depends on how the flat database is designed for each client, right?
No. The reason why the account comes first in that case is because we need the account, like we need the pre-image for each slot, we need to know the address to do the hashing. But I was confused, but I wanted to, bring people's attention to this. Like the order is inverted, but there's a good reason for this, is because you need the address to compute the storage key slot in the target tree.
Right. So the TLDR is that probably we will change the API to flip this order, right?
I don't think we can. Okay, let's take that offline then. But yeah, you see, there's there's a bit of a confusion. We need to refresh a bit on this.
Okay. I think that's everything for today. Thanks everyone, and we'll see you again next time.
Thank you. See you next time.
Thank you for leading. Bye-bye.
Thanks, Mike.
Yeah.
Thanks.